Our next speaker is Debyani Manna, who will talk about restricted H-fold sumsets. Please. Go ahead.
First of all, thank you, Professor Nathanson, for giving this opportunity to talk here. And again, forgive me if my voice breaks, as I've got some severe cold. So now I'm going to talk about some extended inverse results for restricted H-fold sumset in integers. So first, I'll start with some basic introduction, basic definitions. So for sumsets, if for any two subsets A and B of an abelian group G, we have defined A plus B as the elements A from A plus B from B. And a very simple example from of sumsets is if you take any two subsets A and B from a set of integers, what facts can we determine about the subsets A plus B? Now, there is some well-known result of regular and restricted H-fold sumset. So first I define what regular H-fold sumset is. Basically, we are extending the earlier phenomena that A plus B, and we are defining over H-fold A. So this is basically defining like summation over I is equal to 0 to k minus 1 lambda I, where lambda can belong from 0 to h, for I belongs to 0 to k minus 1, with summation from I is equal to 0 to k minus 1 lambda I is equal to h. And for restricted case, that lambda I belongs to only 0 or 1. Now, now, what is direct problem and inverse problem? So direct problem is one we know the structures of the set A and try to determine the structure of the sumset. One very well-known example of direct problem is Lagrange four square theorem, obviously, where any non-negative integers can be written as the sum of four squares. And what about the inverse problem? Inverse problem is one in which we have some information about the sumset and we try to extract some information about the structures of the individual sets. The simplest example of inverse problem is Freeman's theorem, that for a non-empty finite set A of k integers with cardinality of 2A is equal to 2k minus 1, then A must be an arithmetic progression. So here is the direct and inverse result of H-fold sumset due to Professor Nathanson. Let H be a positive integer and A is a non-empty finite set of k integers. Then cardinality of HA is greater or equal to H into cardinality of A minus H plus 1. And this lower bound is best possible, and this equality holds when A is an equality coefficient. And inverse result is, okay, we have this. And the direct result for restricted H-fold sumset is that H and K be two positive integers with H is less equal to K. And A be a non-empty finite set of k integers, then cardinality of H cap A will be greater or equal to H into cardinality of A minus H square plus 1. And for 2 less equal to H less equal to K minus 2 and K greater or equal to 5, cardinality of H cap A is equal to this equality holds when A is a K term arithmetic progression. So in this talk, I'm going to talk about extended inverse problem. So this is again a kind of an inverse problem, but where this where the sumset appear when the sumset deviates slightly from the minimum size. So like we have this optimal bound, and what will happen when the when its cardinality deviates slightly from the minimum size. So Freeman has dealt this type of problem, and he has this theorem that for k greater or equal to 3 be a positive integer, A be a non-empty finite set of k integers, if cardinality of twice of k twofold of A is equal to twice of k minus 1 plus B less equal to 3k minus 4, then A is a subset of arithmetic progression of length k plus B less equal to 2k minus 3. Now, extended inverse problems of H-fold A. So Freeman has studied that, and this is one result that if we have the largest term of largest number of the set A is less than or equal to 2k minus 3, where A is a set of k integers, then cardinality of 2k is greater equal to k plus a k minus 1, the largest one. And if ak minus 1 is greater equal to 2k minus 2, then the twofold sumset of a is greater equal to 3k minus 3. Yeah. Now, Lev generalized the above result for H-fold A, and Tang and Singh, they have proved some extended result, and later on Mohan and Pandey, they have extended this work of Tang and Singh, and they have shown a possible inverse theorem for H-fold A with a range of 3H plus 1, like when the cardinality of H-fold A lie between this H into cardinality of A minus H plus 1 and H into cardinality of A plus twice of H plus 1. Now, recently some extended inverse result for H-fold A has been studied by Rajagopal and Sinia in more precise manner. So one can check that as well. Now, about extended inverse result of restricted H-fold sumset. Well, that conjecture is given by Freeman, and where it is given that if A is a element of A is a subset of k integers where k is strictly greater than 7, such that there is some ordering of the elements with GCD1, then the twofold restricted sumset of A is greater than is equal to ak minus 1 plus k minus 2 if ak minus 1 is equal to 2k minus 5, and 3k minus 7 if ak minus 1 is greater equal to 2k minus 4. Now, Lev has partially proved this above conjecture, where he has said that twofold restricted twofold sumset is greater than is equal to ak minus 1 plus k minus 2 if ak minus 1 greater less than equal to 2k minus 5, and theta plus 1 into k minus 6 if ak minus 1 is greater equal to 2k minus 4, where theta is the golden ratio. Now, in the literature, we have very limited number of results about restricted H-fold sumset. Recently, there is a work of Nathanson, so that actually contains a lot of results. But again, this is not as many as H-fold sumsets. So that in this Nathanson recent works, he has basically raises questions where what can you say about the what can I say about the sets A when that when we have certain cardinalities of H-fold restricted H-fold sumset at M. So in 2023, I think Mohan and Pandey, they have started the extended inverse theorem for twofold restricted sumset and threefold restricted sumset. So in this talk, we are going to talk about the restricted sumset when H is greater than is equal to 3. Now, this conjecture is given by Mohan and Pandey in their earlier work when they have basically started this restricted twofold sumset and restricted threefold sumset. So in this in our recent work, we have basically proved that for H greater equal to 3 and k a positive integer, let A be a finite set of k integers such that minimum of A is equal to 0 and their GCD of the elements of A is equal to 1. So if k is greater equal to 3h plus 1 and cardinality of h cap A is equal to hk minus h square plus 2, then A is a subset of 0 to k. Basically, we want a set A with cardinality k. So here we are basically saying that we will have A which is inside a arithmetic progression of size k plus 1. And when k is greater equal to 3h plus 3 and we have cardinality of h cap A is equal to hk minus h square plus 3, then A would be a subset of arithmetic progression of size k plus 2. And for certain bound of k, which is greater than is equal to 3h plus 4, cardinality of h cap A is equal to hk minus h square plus 4, then A would be subset of a arithmetic progression of size k plus 3. So here I am giving you a sketch of this proof. So for particularly for case 1, when k is greater equal to 3h plus 1 and cardinality of h cap A is equal to hk minus h square plus 2, then we will prove that A is a subset of k plus 1 term arithmetic progression. So let us assume that h is greater equal to 3 and k is greater than is equal to 3h plus 1, and we are taking a1 as a0, ah minus 1, ah, and so on, a k minus 1. So basically, we are removing these elements from a1 to ah minus 2. So our claim is that GCD of a1 is 1. So if not, then that must be greater than 1. So then there exists a positive integer t such that 1 less equal to t less than h minus 1. And we are taking a2 as a0, at plus 1, and so on, ak minus 1, and a3 as a2 minus at. So then our GCD of a2 must be 1 and GCD of a3 must be greater than 1. So for getting a contradiction, we'll show that cardinality of h cap a will be greater than hk minus h square plus 2. Now we have that GCD of a3 will be greater than 1 and a2 GCD of a2 will be 1. So then the sets h minus 1 fold restricted sumset of a3 plus at, that becomes basically h fold, and h cap of a3, that are basically disjoint subsets of h cap a. So now the way we choose t, we'll have h cap a will be greater than is equal to this. Now here actually we have used the optimal bound, we have used the bound of h fold sum, a restricted h fold sumset. So then we will have that would be greater than is equal to hk minus h square plus 4h plus 1. Now I'll have that h is greater than is equal to 3. So this is obvious that this is greater than hk minus h square plus 4. So we have proved that GCD of a1 is 1. Now we are choosing a4 in such a way that we are removing that a0, ak minus 2, and ak minus 1. So then clearly we are taking that h fold thing as a1 plus a2 and ah minus 2 plus 2 cap of a1, and union this h minus 2 cap a4 plus ak minus 2 plus ak minus 1. And again, this is a subset of h cap a, and they only intersect at this point, that a1 plus a2 and so on, ak minus 1. Sorry, a1 plus a2 plus so on, ah minus 2 plus ak minus 2 plus ak minus 1. So we assume that cardinality of h cap a is equal to hk minus h square plus 2. So this would be greater than is equal to, as this is a subset of h cap a. So by some simple calculation, we'll have that 2 cap of a1 will be less than is equal to 2k minus h. And now since k is greater than is equal to 3k plus h, so we'll have this. Earlier we have shown that Leib has proved this result for this certain case where two-fold restricted sumset of a is less than this kind of thing. Then we'll have the okay. So then we'll have that finally we'll have ak minus 1 will be less than is equal to k. Hence a is a subset of 0 to k. Again, the argument for 2 and 3 that can be proved in the same way. Now these are our complete results. Basically, we have given the exact structures of a for certain cardinalities of h cap a. So we know cardinality of h cap a is greater than is equal to hk minus h square plus 1. So hk minus h square plus 1, this obtained when a is an arithmetic progression. So what it could be when cardinality of h cap a is hk minus h square plus 2. So for k greater or equal to 3h plus 1, and a is a finite set of k integers, if this cardinality holds, then a must be 0 to k minus x, where x must be one of this 1 or k minus 1. So this is this calculation is quite easy. If x belongs to 0 to h minus 1, then we must have a would be something like this, and then we basically calculate what h cap a would be, and then we will have that cardinality of h cap a would be hk minus h square plus x plus 1. So here we have taken x as x belongs to 0 to h minus 1. So only for x is equal to 1, our result will hold. In this particular case, again, this is also shows that for the different choices of x, like if we choose x like 2, 3 or something else, so then we'll have different cardinalities. Like h cap a would be like hk minus h square plus 3, 4 and all. So it actually shows for different cardinalities of h cap a, there exists some a for which the existence of a. So this is since this cardinality of sumset, this is translation invariant. So we have basically used this translation, and we finally prove that only this will only hold when x will be k minus 1. But when x is exactly h, then we will have that cardinality of h cap a is equal to hk minus h square plus h. So that means for different choices of h, we can say that there exists some a for which that h cap a is when cardinality of h cap a is equal to hk minus h square plus h whole, then we'll have certain a for that. So now for h is equal to 3, when cardinality of h cap a is equal to hk minus h square plus 3, so then we'll have for k greater or equal to 12, when cardinality of 3 cap a is equal to 3k minus 6, then we will have a as 0 to k plus 1 minus x comma y, where x and y can be one of these sets, 1, 2 or k minus 1 k. And basically you can see that these are the only cases where cardinality of 3 cap a is equal to 3k minus 6 volts. And for for h greater or equal to 4 and k greater or equal to 3h plus 3, cardinality of h cap a is equal to hk minus h square plus 3 wholes, then a will be 0 to k plus 1 minus x comma y, where x comma y is one of the sets 1, 2, k minus 1k, or 2k plus 1 or k minus 2 and k plus 1. Now for cardinality of h cap a is equal to hk minus h square plus 4. For the lower case, when h is like 3 or 4, actually we are getting a lot of sets. But for the higher cases, even in the earlier case also, when we are assuming that cardinality of h cap a is equal to hk minus h square plus 3, then also we'll have different case for h equal to 3, and for h greater equal to 4 we have different result. So again, in this case, for h equal to 3 we have different result. This would be the exact structure. When cardinality of 3 cap a is equal to 3k minus 5, then a must be one of these sets. And again, for h is equal to 4, we have another one, that cardinality of 4 cap a is equal to when 4k minus 12, then we'll have this, the structure of the set, exact set. And we can basically generalize this after 5, for h greater equal to 5. So then we have very less number of sets. So the purpose of this is when we're taking these cardinalities like this, h fold a is equal to hk minus h square plus 4, we have calculated till 4, because after that calculation is become so complex. But if we calculate that after 5 and all, so then we are actually will get that different result for lower cases, and for upper cases, for large h we can generalize. So as a conclusion, we can say that if we take cardinality of a is equal to k, where h cap a achieves, we have basically studied that when h cap a achieves the cardinalities hk minus h square plus 2 plus 3 and plus 4. So in this calculation, here I have not shown that one can see that there exists a set A for certain cardinalities of h cap a in this interval, because h cap the cardinalities of h cap a can exist in this interval. So there exist certain sets for that. Now it is also important to notice that in our results, that cardinality of a, that is k, that depends on h. So we are determining we are not, again I have already said that we are not really determining the results of a for cardinality of h cap a, when cardinality of h cap a is greater than is equal to hk minus h square plus 5 and on. So then in particular in our method, it will take a substantial calculation. But Okay, I'll conclude with some open problems. So we have tried, but we did not really solve it. That where we want to find an extended inverse problem of H cap A, where cardinality of cardinality of A, that is K, does not really depend on H. And another one, if it is possible to find such key for which H cap A and HA both hold, both not holds actually, both there will not get some A for certain cardinalities of H cap A and HA for the same T where T belongs to this. Is it even possible or not? So this is the thing. So these are the references, and thank you for your attention.
Thank you very much. Are there any questions from the Zoom world for our speaker?
Okay.
If not, we thank Debyani again, and the next talk will be in 3 minutes.
Thank you. Thank you.
Thank you very much. Very nice.
Yeah. Thank you.
So Chihar Yip is here. If you can share
Yeah,
your slides, that would be great.
yeah, sure.
Good. Just a minute or two.
Okay.
How long have you been in Hong Kong?
Just for 1 week.
1 week. Okay.
I just
I
moved
thought
to
it was
Hong
not a
Kong.
long time, but I didn't realize it was such a short time.
Mhm.
Yeah.
So should I start at 10:25 or 10:30?
Oh, sorry. Yeah, you should. You'll start about 10:30
Okay, 10:30.
because
Sure.
that's what the schedule says, and I try to adhere to it.
Okay. Mm.
So you can answer the question I was going to ask you, which is everywhere I talk to people, mathematicians, they or their colleagues are using AI to help with proofs of theorems. And according to the Economist magazine, there is a completely free Chinese AI system, which is as good as any of Anthropic's systems, or it's supposed to be really very, very good. And I was curious about the experience of mathematicians trying to use one of those systems to prove a theorem, because everyone I know uses, let's say, ChatGPT or Aristotle or one of the American systems. But this is really going to be very interesting to see. You can imagine a great competition, which is which country's AI will first solve the Riemann hypothesis. That's the challenge. What time is it now where you are?
Like 10:30 p.m.
Oh,
Like
that's
around
not so
10:30
bad.
p.m. Yeah.
I try not to have talks not scheduled for 2 or 3 in the morning where the speaker is, but it's not always possible, but doing fairly well this year. What is the language of instruction at the universities in Hong Kong? Is it English?
English. Yeah, at least math courses are taught in English. I mean, but maybe some like history courses or like social science courses are probably taught in Chinese.
But at least for undergraduates, are
Yeah.
some courses taught in Chinese for students who do not speak English?
For math courses, everything is
Yes,
taught in English.
in English,
Yeah,
even
yeah,
the even the lowest level classes.
yeah, yes,
Oh,
that's right.
that's interesting.
Yeah.
Okay.
Mhm.